Okay, here is the homework tab, and all the way at the very bottom, practice exam number 5 for the final exam. 17 questions, ranging from basically chapters 2 through 11. Going back to chapter 2, one type of chart we created there were called dot plots, where for each value given to you, you put a little dot on a number line. Since you don't have to create the whole chart yourself with every single number, you're just comparing multiple choice, which one's the answer. I look for differences like at the 80 value. Here there's one dot under 80, here there's 2, here there's none, here there's 4. So if I just look for the 80s, how many 80s are in the list? There's 2 of them. It's got to be C by default because it's the only one that has 2 dots on 80. And if there was more than one with 2 dots, then I would check another number like 70 or 85 or something like that. So once you have your chart here, if you kind of trace it with the cursor, it does appear to form a bell shape. Although there is a distinguishing feature that there's a big gap right here and one little dot all by itself way out at 50. So that's kind of the definition of what an outlier is like, is when you have one value far from the rest. But even with that, if you trace the shape of this graph with a pencil, it would have a approximately bell shape to it. So does the configuration of points appear to suggest that the volumes are from a population with a normal distribution? The good thing for that is it doesn't have to be perfectly normal. As long as it's close, you can say yes, this is approximately normal. So yes, the population appears to have a normal distribution because the dot plot resembles a bell shape. Are there any outliers? And yeah, that's the point, is even though it is bell-shaped and normal, and we could do normal distribution stuff with it, we always have to worry in statistics about outliers. They can cause problems for us. So this 50 is an outlier. We'd want to be aware of that as we're working on whatever stuff we were going to do with this. But 50 is definitely an outlier because it's far from the rest of the data. Another type of chart is a stem leaf plot, which is basically a dot plot turned sideways, and instead of putting a dot for every value, you actually put the values of the numbers. So by looking at the 9s here, there's a 9, 0, 9, 2, and a 9, 7 in choice A. Choice B's only got a 9, 1, and C's only got a 9, 1. So how many 90 numbers are there in the chart? In the actual data, there's only one 90. It's 91. So it can't be A because that's got 90, 92, and 97. Another difference I noticed is in the 1-4s, the 140s, B has a 1-4 with a 0 and a 2, and C's only got the 1-4 with a 0. So either there's 140 and 142 or just 140. There's the 140. Any other 1-4s? No. Yeah, there it is. There is a 142. So it's B. Both 140 and 142 are in the data. So again, at least you don't have to make the whole stem plot if you just look for some differences. Now this is worded backwards from the other problem. It says, is there strong evidence suggesting the data are not from a normal population? Are from a population with a normal distribution. So that's kind of what we do, is as long as it's close to normal, we'll assume that, unless you see strong evidence that it's clearly not. A graph like A is definitely not normal because all the values are virtually the same. This is what's called a uniform distribution. It's not bell-shaped. But B it's not perfectly symmetrical towards the middle, but it's pretty bell-shaped with a high majority in the middle and both ends are kind of low. If you kind of trace the shape of this graph and then think of turning your head sideways and looking at it the other way, it would be approximately bell-shaped. So is there strong evidence that it's not? No, there is not. This is kind of done in a negative way. No, the distribution is not dramatically far from a normal distribution with a bell-shaped. So there is not strong evidence against the normal. So therefore we can assume that it's approximately normal, unless we get strong evidence that it's not. So that's the reason that question's kind of worded in a negative fashion. Okay, with problems like this, I would just take a graphing calculator and go under Stat and Edit, where you get to those lists L1, L2, L3. and enter all the data into list 1 and list 2. I would put all of Terry's numbers in list 1, and then put all of David's numbers in list 2. And then once I have them all in there, you're going to do this that we've done before, where you press stat and go, well, we want to, it says find the mean number. So instead of just stat, we're going to hit second stat. And then if you go over to math and then go down to which one you want to do, there's a third and a fourth one. The third one says mean and the fourth one says median. So that's all I'm doing is second stat, go over to math, and then choose the one you want to do. I want to do the mean first. The mean for Terry. Press enter to select the mean. And then you have to tell it which list you want. So then I would hit second and the number 1 to tell it the mean of list 1. And the calculator says the answer is 3.9 for that. Or you can do it the old-fashioned way and add up all the numbers and divide by how many there are. Either way you'll get 3.9 for that. The median for Terry's books is same thing. Second stat, go over to math, go down to the median instead of the mean, and again tell it list 1. I just did that in the calculator and it said the answer is 2. Or you can put the numbers in order and try to find the 1 or 2 numbers that are in the middle. A median is the value in the middle. Then repeat the same stuff for David. So I'm just going to give the calculator the command to do the median and the mean for list 2. So the mean for list 2 is 2.5. And the median for list 2 is 2. Sorry about that. Both distributions have a median of 2, so they're centered around the value of 2. But Terry's average or mean is higher, 3.9 versus 2.5. And you can see that from the numbers. David has all numbers that are 1, 2, 3s, and 4s. Terry has 1s and 2s, but he also has a 7, an 8, and a 10, and a 6. So because he has some values that are much larger than the rest, that's exactly what this problem is showing, is that the median's unaffected by larger values or smaller values, or even an outlier, even if you had a single large value or small value. So both of them have a median of 2, but Terry's average or mean is much higher because of these larger values. The mean can be affected by 1 or more values that are different from the rest. So does there appear to be a difference? Yes, there is a difference. You can't see that from the median, which is why it's never good to just look at one measure in statistics anyway. But yes, based on the results, words in Terry's books are longer than words in David's books because his or her mean is larger for Terry. And you wouldn't see that from the median because they're both the same. Okay, quartiles can be found. They want the third quartile here. So the best way to handle this, if I can do this so you can see what I'm pressing. In the calculator, I'm going to put all the data in first. So stat and edit. Here's all the data I just had in there. I'm going to clear out these two. Type in all the numbers first. So let me just do that because it'll be quicker. 31, 32, 32, 32, 36, 38, 40, 42, 44, 44, 44, 44, 45, 45, 47, 48, 50, 55, 59, 67, 68, 69, 70, and 80. So luckily they are in order already. Again, on a test I would go a little slower than I just did and maybe go back and double check all the numbers and make sure you didn't have a typo. So you can get the quartiles by simply pressing stat, and if you go over one to the right at the top where it says calc, the very first choice, 1 var stats. And then I'm going to press enter to do it. Or some of you have those calculators where you have to hit like it's like more user-friendly, where you tell it which list you want, and then it'll have you paste it. But then it'll just come up like this. Notice there's a down arrow at the end where it says n equals 24. That means there's 24 numbers. If I down arrow 5 times, 1, 2, 3, 4, 5, this is that 5-number summary that box plots are made out of. And it's got the minimum value, the smallest one, 31. Q1 is the lower quartile, 39. The median's 44.5. Q3 is the upper quartile, 57. And the maximum value is 88, the largest one. This question only wants the third quartile, so I can just tell it it's 57. Now you can do this by hand too. If you separate the values in half, there's 24 numbers. So if you get the top 12, cut it in half so there's 12 below and 12 above, then you just find the median of the 12 highest numbers. So it would actually be an average of 2 numbers, and that'll come out to 57. So it must be between 55 and 59. The halfway point of that's 57. So you can do it by hand or by calculator. Okay, moving to another chapter. Probabilities came up in chapter 3. And the main rule about probability is that it has to be between 0 and 1. So 0.07 is fine, 0 is fine, 5/3 is no good because that's bigger than 1. 1 is okay, square root of 2 is about 1.4. That's too high, it's bigger than 1. Negative numbers are never good. 3/5 is okay, 1.37 is too large. You just check all the ones that are impossible. You can't get negative and you can't get bigger than 1. You toss a coin and randomly select a number from 0 to 9. What's the probability of getting tails and selecting a 4? So we have 2 independent events. Getting a tails has a 1/2 probability. Selecting a 4 out of 10 numbers is 4 out of 10 or 2 out of 5. So I'm basically multiplying 1/2 times 2/5. And if you do that with a calculator by hand, 1/2 times 2/5 equals 1/5, which is 0.2. Oh, and I read that wrong. We're not selecting 4 different numbers, we're selecting a 4. So a 4, there's only one of those out of these 10 numbers. So it's 1/2 for the tails and 1/10 for the selecting the number. 1/2 times 1/10 is 1/20th. And as a decimal, that's 0.05. So if you have an AND problem, you can just multiply the answers together as long as they're independent of each other, which coins and selecting numbers don't affect each other. Okay, 13 of 100 digital video recorders in an inventory are known to be defective. What's the probability you select one that's not defective? So 13 out of 100 is 0.13. And then not something, the probability of not something is 1 minus the probability that it does happen. So if you do 1 minus 0.13 in a calculator, the answer will be 0.87. It's kind of like saying if there's a 13% chance of rain today, then there's a 87% chance it won't rain today. The opposites like that, they're always just 1 minus each other. That's called the complement. Okay. In chapter 4, we did these, how many different ways you can do something, the number of different ways to do something. There's 2 main ways to calculate these, permutations and combinations. So here we have a case where there's 12 wires, that's my total number, and I want to test 3 of them at a time. So this is either going to be 12 permutation 3 or 12 combination 3. The difference is whether order matters or not. And since I'm testing all 3 at the same time, the order really doesn't matter. So this would make this a combination. Permutations is when order matters. Combinations is when they don't. So in your calculator, you can you put the bigger number first, 12. Press the math button. And you right arrow over to probability, PRB. Permutation and combination, they're the second and third choices. In this one, I'm going to choose combination because the order doesn't matter. And then you put the smaller number last. 12 combination 3 is 220. 220 different ways you could have this happen. So if you had to test every possibility, it would take you 220 tests to check every possibility. Okay, moving to chapter 5, we had binomial probabilities, two main kind of problems here. They give you a number of trials, 5. They give you a probability of success, 0.05. And then the question can either be, what's the probability of exactly so many numbers, or what's some kind of inequality of that? Question 9 says, what's the probability of exactly 3? Exactly binomials are done with PDF. So this is one thing you have to practice before you take the test, is knowing where everything is in the calculator, because we've already seen times where we hit stat, second stat. I just did one with math. This one is second vars. And that's where the normal CDF is that we use a lot too. But if you up arrow, you'll see binom PDF and binom CDF near the bottom of all the choices. For this problem, since it says exactly 3, I'm going to choose binom PDF. And mine is the version where you type all the numbers in. Some of you have calculators where you paste in all the answers. So you put the number of trials first, 5, then a comma. The probability of success needs to be between 0 and 1, 0.05. So if you tried to put like 5% here, it would be wrong. Comma, and then exactly 3. Doing exactly with a PDF. They want this rounded to 3 decimal places, so 0011. We're going to stop after the 001. 001, and we don't need to round up because the next digit's also a 1. That's how you do an exactly binomial. Then here it says, what's the probability that more than one experiences headaches? So this is an inequality situation. We still have an n of 5, although the p is different now, 0.6767. More than 1 literally means 2, 3, 4, and 5. 2 and higher. Now if you want to do a PDF for 2, a PDF for 3, a PDF for 4, and a PDF for 5, you could do that. But you'd have to add all those answers together. The CDF version of binomial will let you do a bunch of answers at once. Unfortunately, it only works if you go from a number down to the bottom, down to 0. So here's a perfect example of where I want to use the complement, like that problem 2 problems ago, where they said 13% are defective, what's the percent that are not defective, and I did 1 minus it. Same idea here. If I want to calculate 2 through 5, because that's what more than 1 is, and I can't do that all at once, I could do the complement. The complement or opposite of 2 through 5 would be 1 through 0. And to do binomial CDF, you have to do some number down to 0. So by doing a binom CDF, second vars, up arrow till you get to binom CDF, I'm going to do it as if I'm doing the opposite of what the question wants. I'm going to tell it n is 5, p is 0.767, and if I tell it 1 at the end, with CDF and a 1, this will calculate the probability of getting 1 or 0 headaches. But that's exactly the opposite of what I want. I want 2 through 5, not 1 through 0. So that's where you do the complement. The complement's 1 minus whatever you got, and that'll give you the probability of 2 through 5. So the probability of 2 through 5 is 98%, almost 99%. The probability of 1 through 0 is a little over 1%. They're exact opposites of each other. The question wants more than 1, the 2 through 5, so the actual answer is 9880. 9880 is the probability of more than 1, because that's the 2 through 5. It's just you have to do it backwards because the calculator can't do 2 through 5. It can only do something down to 0. They had to program it one way or the other, and they chose to go downward. Okay, so is it reasonable to expect that more than one subject will experience headaches? And clearly, with the probability being so high, the answer to that is yes. There's a 98, almost a 99% chance that you're going to get more than one person experiencing headaches. So that is reasonable to expect it to happen. It's almost assured to happen. Now, sometimes you have to read these and they're kind of worded differently than what you would expect the answer to be. Is it reasonable to expect? The answer is definitely yes. It's A or D. This is a very high probability. It definitely is likely to happen. But they word this kind of backwards. It says, because the event that the number of subjects that experience headaches is less than or equal to 1 is unlikely, or that that's not unlikely. So, and they're getting to, that's kind of what the idea of a p-value is once you get to chapter 7 and beyond. So again, they're referring to, even though we can say it both ways, the 98% is very likely, so that's a yes for that reason. Or looking at the other version, getting less than 1 headaches is 1. And that's an unlikely one. And they're wording this from that point of view. The one of getting less than or equal to 1 is unlikely, because the less than or equal to 1 probability is only 0.01. And remember how if you're less than 0.05, that's considered unlikely. So this answer is A, only because they're wording it backwards. They could have said it yes, because the probability of more than 1 is likely, or you can say the opposite, less than or equal to 1 is unlikely. That's really saying the same thing. More than 1 likely is the same thing as saying less than 1 is unlikely. And the only reason they're doing it backwards is because that's how p-values work when you do hypothesis testing. Okay, moving on to chapter 6, where we do normal CDFs. There's two kinds of problems here. You got to watch out with the central limit theorem. If there's a sample size, that affects the standard deviation at the end. And here there is, because they've got 35 passengers. So we have a sample of 35. If the average weight on the aircraft is greater than 165 pounds, then the aircraft could be overloaded and that could cause a problem. So they would be worried about, we don't want to overload it and maybe the plane would crash or something. So the probability of being greater than 165, using a normal problem, because this says assume weights of men are normally distributed with a mean of 173.4 and a standard deviation of 37.2. So normally what you would do here is you want to do greater than 165, so you do normal CDF, you'd put in the 165 first as a smaller number, then you're literally going to infinity, so you'd use 10,000 second, and then you'd put the mean third and the standard deviation fourth. If they hadn't mentioned 35 passengers, that's what I would do. But since there is 35 passengers, you make one slight adjustment at the end. So first start off like you're doing just a basic normal CDF. Second, vars. Normal CDF is right near the top, the second one down. We never use normal PDF. And I'm doing greater than 165, so 165 to 10,000. Unlike the binomials, we can do from a number up to the top. So from 165 to infinity, and then you put comma, and then you put the mean third, 173.4. And then normally I would put the standard deviation fourth, 37.2. If there's no mention of a sample, then you're done right there, press enter. But if there ever is, and this is on the formula sheet, the central limit theorem, you have to divide the standard deviation by the square root of the sample size. So I have to divide by the square root of 35. You just tack that onto the end. And round to 4 decimal places, 9092. 9092. So that was all what the central limit theorem was about in chapter 6. Should the pilot take action to correct any overload? Well, since the probability of an overload is over 90%, that's alarming. So yes, the probability is high. The pilot should take action by reducing the weight somehow. Because this is saying there's a 90% chance the plane's going to be overloaded and that could cause a problem to the plane. So why test fate and mess with that? Okay, chapter 7 is doing confidence intervals. And you can do this by hand or by calculator. First of all, there's two samples going on at once. Two different 40 patient samples. One gets a treatment with magnets and the other one gets a placebo, basically a treatment without magnets. A fake treatment. So do the magnets make a difference or not? The average for the 40 people that got magnet treatments, they had a mean of 5 and a standard deviation of 2.3. The ones with the sham treatments got a mean of 4.6, a little bit less, and a standard deviation of 2.7. So from a sample mean alone, you can't just say, yes, 5 is higher than 4.6, so therefore the magnets work. You really need to look at this from the long run, and the standard deviation plays a role. So we're going to create a confidence interval for each one of these. First, they want a 90% confidence interval for the ones that got the magnet treatment. And this is a mean because they got mu here in the middle. And you can do this in your calculator since the data is given. You can go to Stat and Tests. And we did all these tests in Chapter 8 and 9. Go back to Chapter 7. You can do confidence intervals by hand, or even the calculator will handle them. And now that you know how z-tests and t-tests work, you might be able to handle this better. This will be a t-interval similar to a t-test because the sample standard deviation is given. They didn't give me sigma, all I have is s. So in means, you always pick t when you don't know sigma. Put it on stats because they gave me all the stats. The x-bar sample mean was 5.0. S was 2.3. The sample size was 40, and they want a 90% confidence interval. So put 0.9 for that. Calculate. At the very top, it'll give you the confidence interval. 4.38, comma 5.6. So that's interval notation from college algebra. It says round to 1 decimal place. So my lower limit is 4.4, my upper limit is 5.6. So that's how this is interval. That was interval notation. Here's inequality notation, where you put the 4.4 is less than mu is less than 5.6. It's just two different ways to write the final answer. So we're saying that we tested 40 patients and gave them this magnet treatment. We think the real average pain amount that they're reporting is somewhere between 4.4 and 5.6. The sample average was 5, but we think the population average will be somewhere between 4.4 and 5.6 with 90% confidence. Now do exactly the same thing for the sham treatment. They had 40 patients, but their mean and standard deviation were different, so that's going to affect the answer. Do it again, stat, tests, and choose t-interval. So now the mean drops to 4.6, the standard deviation raises to 2.7, everything else is the same. Now we think the average for them is between 3.9 and 5.3. 3.9 and 5.3. So it's lower down the number line. 3.9 is a little lower than 4.4. 5.3 is lower than 5.6. It seems like their average is lower. But the problem is, and this is why confidence intervals are so nice, is that this whole range, the average could land anywhere in between there. So what if the first average was at the lowest limit, 4.4, and the second average was at the upper side, 5.3? You could make an argument that the sham treatment actually works better, just based on that alone. Or it could be 3.9 for this one and 5.6 for that one. So in order for you to prove that the treatment makes a difference, you would need one confidence interval to be entirely above or below the other one. So if this one goes 3.9 to 5.3, we would need the other one to be starting higher than 5.3 and being entirely above it. That's what it would take to show that the treatment makes a difference. Because these confidence intervals overlap, it appears the magnet treatments are no more effective than the sham treatments. So you won't be able to show that there's an effect unless you get one confidence interval entirely above the other one, and that didn't happen here. They do overlap a little bit. From 4.4 to 5.3, which is most of both intervals, they're overlapping each other. So that means either average could end up being higher. And if the magnets are going to make a difference, we would need them to have a significantly higher average, and they don't. So that's kind of another way of doing a hypothesis test, is looking at confidence intervals. They kind of tell you the same thing. Okay, then moving on to the chapters where we do confidence or do hypothesis tests. Here you have a significance level, alpha is 0.05. That's, again, the probability of a type 1 error. And the claim is that the proportion of male golfers is less than 0.8. So since the claim is less than, we would put that in the alternative hypothesis. It doesn't have an equal to in it, it would need to go in the alternative. So the alternative would be less than 0.8, p is less than 0.8, and therefore the null hypothesis would be the opposite of that, greater than or equal to 0.8. Or you could just put equal to. But since the claim is going in the alternative hypothesis, whenever the claim's in the alternative hypothesis, then your goal is to try to support the claim. If it's in the null, you try to reject the claim. The p-value is 0.002. That's a very small p-value. It's definitely less than 0.05. Regardless of where the claim is, we're going to reject the null hypothesis. Reject the null or fail to reject the null, it's definitely reject the null, because the p-value is less than alpha. That type of conclusion is done in every type of hypothesis test, regardless of what test it is and regardless of whether you're trying to reject or support the claim. But if a claim is in the alternative hypothesis when you have a less than or a greater than in the claim, then you're trying to support it actually. And since we rejected the null, there is sufficient evidence, but there's sufficient evidence to support the claim, not sufficient evidence to reject the claim. If the claim had been equal to 0.8, then there would have been sufficient evidence to reject the claim. But we're going to choose A, sufficient evidence to support the claim, because the claim turned out to be in the alternative hypothesis. Okay, so now we're doing a hypothesis test. All the steps, that was just 1 or 2 steps of it. Now we'll do all the steps. So first of all, test the claim that the 2 samples are from populations with the same mean. So same mean means that mu1 is equal to mu2. So it's either C or D. So the alternative either needs to be not equal to, greater than, or less than. Well, they didn't mention anything in the problem about it being greater than or less than. So if it's ever just generic like this, then you always put not equal to in the alternative. There would need to be a clear statement like the last problem said less than for you to pick something like that. If it's just generic like test the claim that they're the same, then the alternative is always not equal to. So now we know the null and alternative hypothesis. The problem has summary data up here in this box in the far corner. Oops. They're giving us summary data right here. So then I can put this in my calculator. And this is definitely a 2-sample problem because they have mu1 equals mu2. If it was a 1-sample problem, they would have numbers here. And because the chart gives S and not sigma, and I'm dealing with means, then I have to do t-tests again. So this would be under stat and tests, and I'm going to choose the 2-sample t-test because there are 2 samples, and it's about means, and I have to use t because sigma is not known. Make sure you're on stats and not data. The first average, the first x bar is 2.39. The first S is 0.65. The first sample size is 27. And I'm just reading this from that chart that had all 6 numbers. The second x bar is 2.62. The second S is 0.96. And the second N is different than the first one, which is fine, 40. We chose mu1 is not equal to mu2 for our alternative, so we'll just keep it highlighted there. And then you always get this with 2-sample t-tests that says, should you pool the standard deviations? Pooled, no or yes? Always click no unless they say in the problem that you can assume the population variances are equal. Well, this problem says, assume the 2 samples are independent, simple random samples selected from normal populations, and do not assume that the population standard deviations are equal. So it even clearly says do not assume that. You have to assume that in order to say yes. If a problem says do not assume it, or if it doesn't mention it, then you would click no. So we're definitely clicking no here because they said no, don't assume that. Calculate. Here we can get our t-score and our p-value. The t-score wants to be rounded to 2 decimal places. Negative 1.169, so that'll make it negative 1.17. Negative 1.17. And then the p-value wants 3 decimal places. P-value is 0.2465, so that 5 is going to bump it up to 247. 247. Since that p-value 247 is greater than the level of significance given in the problem, which is 0.10, 24% is bigger than 10%, that's when we fail to reject the null hypothesis. Since the claim is that they're equal, the claim is in the null hypothesis. So now we're trying to reject the claim. We fail to reject the null. There is not sufficient evidence to warrant rejection of the claim. This is C. And then you can even do a confidence interval. And since this was a 2-sample z-test, I can do a 2-sample z-t interval. We just did a 2-sample t-test. So go to stat, tests. Instead of 2-sample t-test, go to 2-sample t-interval. And all the data is the same. They still have it here, I think. Yeah. 2.39, 0.65, 27. 2.62, 0.96, and 40. Same data that's here in this little table. And the confidence level, it said, well, they didn't give us one, but since we're using a 10% significance level, 10% is the outside area, so that would mean the complement of that would be 90%. If there's 10% on the outside, there's 90% on the inside. Confidence intervals are about what percentage is on the inside. Again, we're clicking no to pooled because it said so in the problem. Calculate. So here comes my confidence interval. Negative 0.55 to positive 0.098. Round to 3 decimal places. Negative 0.558 and positive 0.098. And here's that deal again that we saw on the other test. One of these intervals, the beginning of the interval is negative 0.558, and then the other interval is positive 0.098. So when one side is negative and the other side's positive, you don't know which one's bigger. If it's negative, that could mean that the first one is smaller. If it's positive, the second one is smaller. So we can't tell if the treatment or the placebo is higher. This is a way to show that there's no difference in the treatment versus the placebo. And we saw that with the confidence interval when we failed to reject the null because the p-value was high. So we can't reject the null. The null was that they're equal to each other, so it doesn't prove that they're equal to each other. But we can't say that they're different. So in order to show that a treatment makes a difference, you have to be able to reject the null and say that there is definitely a significant difference. We can't say that here. Okay, then the last 3 problems, we move on to the chapter 10 and 11 that you didn't have a specific test over. So if you tried the homework for this, then you can know how to do some of these things. One thing we do in chapter 10 are scatter plots and correlation. So what I would do is go to your list 1 and list 2, put the x values in list 1, 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, and 5. And then the y's are 7.45, 6.77, 12.74, 7.11, 7.81, 8.84, 6.07. Just watch out for typos. 5.39, 8.14, 6.43, and 5.73. So I just put all the numbers in list 1 and list 2. Stat and edit. You can do some of these charts under second and y equals where it says stat plot. Stat plot, press enter to go into the first plot. At first your plot will probably be turned off like this, where off will be blackened. While it's flashing on the word on, press enter to turn that plot on. Down arrow to the type of graph, and I'm just going to choose the first one. It's already chosen, it's blackened. If it wasn't, press enter. The first graph is a scatter plot. X list is L1, that's where I put the X's. Y list is L2, that's where I put the Y's. The mark just means how do you want the points to show up? Do you want squares, pluses, or dots? Normally we use dots in a scatter plot, but the dots are so tiny they're hard to see sometimes. For the calculator, you're just going to compare this to the answer. It really doesn't matter what you choose. I usually just pick squares or pluses because they're easier to see. Once you have it set up, you can graph any of these statistical graphs by hitting zoom. Zoom is the middle upper buttons. Zoom and the number 9. Zoom 9 does statistical graphs. Here's a scatter plot. All the points are perfectly lined up except for one is kind of higher up. So here's another case where we have an outlier that's kind of far from the rest of the data. And it's kind of the one point that's kind of messing us up from having perfect data here. But that happens in real life. Michael Phelps is an outlier, and we don't want to get rid of him because he's pretty good. So you can't just get rid of an outlier because it messes up your graph. It's actual real data here. So line this up to the 4 choices, and you can see this is graph C where it's lined up except for the one value really high up. This is graph C. That's what the scatter plot is. And it's good to see that because now we can see from the graph that there's an outlier. When we do calculations, the calculations don't always show that there's an outlier. The linear correlation measures how strongly 2 variables are related. It can be strong, moderate, or weak, and it's always a value between -1 and +1. The closer you are to +1 or -1, the stronger the correlation is. And the best way to do this is also in your calculator. You can get correlation by going to Stat. Let's turn the calculator on first. Stat, Calc, and if you go down to the 8th one, it says Lin Reg A plus BX. This is linear regression. A plus BX. There's a one in number 4 too. Linear regression AX plus B. That's more for algebra. In statistics, we write it A plus BX. And then either paste the answer or press enter. And it gives you A and B are the y-intercept and the slope of the equation. R squared, you don't need to worry about. That's taught later in chapter 10 that we didn't cover. And R, that's the one we want, correlation, 0.815. Now, the first time you run one of these in a calculator, the R squared and the R don't show up. You might only see A and B in your calculator. You only have to do this once and then it'll be there every time. If you press second and the 0 button, this is called catalog. It's literally an alphabetical listing everything the calculator does. So it starts with the letter A's. Hold the down arrow, just hold it down and you'll see the cursor fly by. A's, B's, C's. When you see letter D's come up, let up. And then go down until you get to one that says diagnostic on. For some reason the calculator defaults to diagnostic off, which doesn't show the R squared and the R. And I think it does that because in algebra they don't need those, and it's easier to tell statistics students to turn this on than to tell algebra students to ignore it. So go down to diagnostic on and just press enter twice, once to select it and once to do it. It'll say done. Now anytime you do stat calc number 8 and press enter, then you'll get the R to show up. And you won't have to do that more than once. Once you do it once, it's done now. Your calculator will always show R now until you clear the memory of the calculator. So if you have to do another problem, at least R will be there now. So my R is 0.8158. Round to 3 places, so I'm going to say 816. When correlation is above 0.8, 0.8s and 0.9s, that's good. The closer to 1 you get, the better. If you are above 0.8, then you have strong correlation. And then you can say there is sufficient evidence to support the claim of a linear correlation between the two variables. There is a linear correlation between them. One variable can be used to predict the other one. The danger, though, is sometimes predictions are off when you have these unusual points. Another thing that could affect us is if we have a curved graph like D. In a graph that's curved, you might also get a R value above 0.8, but then predictions aren't so good. So that's two things we look for. Is the data curved in some fashion? Is there an outlier? Then predictions aren't the greatest. We can still say there's a linear correlation like we did in this answer, but it says identify the feature of the data that would be missed if you didn't look at a scatter plot. The scatter plot reveals a perfect straight line pattern except for the presence of one outlier. And that's what we don't want. This is kind of going to throw us off a little bit by having that there. But at least it's still strong enough to say that there's a correlation between them. If you get below 0.8, then your correlation's moderate or weak, and then predictions are definitely no good. But if it's above 0.8, then you can at least try to make some kind of prediction. Just watch out for curved data and outliers. That's Chapter 10, the only thing you have to know for Chapter 10. 2 questions for Chapter 11. Chi-square tests here. And this one, they actually give you the calculator output for the test statistic and p-value. And just like we had z's and t's before for means and proportions, in these chi-square problems you get a test statistic called a chi-square value. It's kind of like a z or a t-score. We have the home team and the visiting team, and then there's different sports: basketball, baseball, hockey, and football. So the question is about, in chi-square tests, it's about, are these two different categories independent of each other or not? Does the sport you play affect how well home field advantage is? Possibly or not. And so the null is always that they're independent of each other. The sport does not affect how well you win at home. The alternative hypothesis would be that they do affect each other, that they're dependent on each other. So if we look at the p-value, the p-value is 0.47. That's a very high p-value. It's way above the 0.05 that they're giving us in the problem. Use a 0.05 level of significance. You need to get a p-value less than 0.05 in order to reject the null. We did not, so this is where we fail to reject the null, just like all the other hypothesis tests. Fail to reject the null because the p-value is greater than alpha. Fail to reject the null that wins are independent of the sport. So it appears that home field advantage does not depend on the sport, since we failed to reject. When you fail, then there's not enough evidence, insufficient evidence. If you reject, then there is enough evidence to say that. And then the last question, you get to do the same thing, except now you have to take the data and get the p-value and test statistic yourself. So we've got a 2x2 chart. We've got white and minority candidates as one category, and whether they passed or failed an exam. So is passing independent of race, or does race play a role in it, is what we want to try to show here. So there's 4 numbers in the chart: 16, 19, 7, and 22. You can do this in your calculator if you employ a matrix. Matrix is found under second and the x to the negative 1 key. Right above that it says matrix. So that's why you have to hit the second key first. Second and the x to the negative 1 key gets you to matrices. First go over to edit. Right arrow over to edit, because we have to put the data in the matrix first. Press enter on matrix A. The size of a matrix from algebra is how many rows and columns you have. This one has 2 rows and 2 columns. So I press 2 enter, 2 enter. Then it lets you put the 4 numbers in. 16 enter. 19 enter. 7 enter and 22 enter. Make sure you press enter on the last one, because the 22 is down here, but it's not there yet. I have to press enter. Now it's there. Once you get all 4 numbers in there, it's real easy to do this test. You press stat, Go over to tests. We've already used z-test, t-test, 2 sample z, 2 sample t, 1 prop z, and 2 prop z. Those are the 6 main types of tests. We've even used some of these intervals too, for confidence intervals. Then there's right below that, there's one called chi-square test. Be careful on your calculator. Some calculators also have a chi-square GOF test. You don't need to know that one for this exam. So some calculators have it and some don't. This one doesn't have it, which is fine. Whether you have it or not, everybody should choose chi-square test alone, not the GOF one. And you don't have to do anything. Literally, it says observed are in matrix A, expecteds are going to go in B, but the calculator does them for you. You literally don't have to do anything except put the data in the matrix and hit calculate. Chi-square is 3.2069. The p-value is 0.73. And since 0.73, the p-value, how does that compare to 0.01? 0.7 is bigger than 0.1. Now, if they would have given me a 10% level of significance, then I would be less than it, and I would reject the null. But since it's higher, then we're going to fail to reject the null. The null should be that they have the same chance of passing, which is either A or C. And then the alternative would be that they do not have the same chance of passing. So this is A. The null is that they're equal, and the alternative is that they're not equal. The null is that they're independent of each other, and the alternative is that they depend on each other. Chi-square was right in my calculator. Round to 3 decimal places. That was 3.207. Oops. 3.207. The p-value was in the calculator. 0.0733 to 4 decimal places. 0.733. And since 0.7 is greater than 0.1, there's not sufficient evidence to either support or reject the claim. So we have to check, is the claim in the null or the alternate? Results from a civil test are shown. Is there sufficient evidence to support the claim? So there's not sufficient evidence to support the claim. The claim must be in the alternative hypothesis that race makes a difference. So this is saying that's not true. There's not sufficient evidence to support the claim that results are discriminatory. So there could have been a lawsuit going on, somebody was claiming discrimination, and we don't have evidence of that here. Apparently the different races are passing the test at an equal proportion, roughly. Okay, so there is practice exam 5, all 17 questions. The final exam is very similar. Email me if you have any questions as usual. Good luck on your final exam.